So hello to everybody. Uh, I would first of all like to uh, thank the organizers for this conference. From my personal experience, sometimes organizing an online conference, especially when you have to change dates several times, can be more time consuming than a null style real life conference. That is why I really appreciate all the effort, all the time and energy you put into this conference. So the three of you, you did really a great job. Thank you very much. And let me start my talk. So I will present some recent joint work with Leandro Vendramin. And I will start with a short version of it where I will try to explain to you what we have done and why we have done this. And then there will be a longer version where I will give more details and explain how we did the things I'm talking about. So I will start with something you have seen already a couple of times uh, today and yesterday. So we start with a solution. By a solution, I will always mean a set theoretic solution to the Baxter equation. And if your solution is, let's say, left non-degenerate, then out of it you can construct a derived solution, which is another solution to the Baxter equation, which is usually simpler. And there is one more thing you can construct out of a solution, which is its structure monoid or structure group. That is one more simpler thing which you construct out of your complicated solution. Monoid or group, depending, you need some more conditions for the group to be constructed. And you can make the same thing out of your derived solution. You can also construct your structure monoid or group. And the most interesting thing actually happens in between. There will be a map, a very explicit map, going from the structure monoid group of your solution to the structure monoid group of your derived solution. It will be bijective, and luckily it will not be a monoid group map, because if it had, well, it would mean that you have more or less twice the same group. But this is something more subtle, which is a group or monoid one cocycle, which means that you have two strongly connected monoid group structures, and one way of translating the thing that you have a one cocycle is saying that you have a brace. So this is actually one of the possible ways of thinking about braces. So I will recall this explicit map, which I put in brown in more detail, even though it was mentioned a couple of times, because my secret goal is the permanent secret goal of all my talks. It is to advertise the graphical calculus, advertise the diagrammatic calculus. I'm actually very lucky because you have already seen a talk by Shan Majid where there have been a lot of graphical calculus and where you have seen that it can give very interesting things. And this will be fundamental for my talk as well. And now, after that, I will recall one more classical thing, which is slightly less known to this community. So I will start once again with a solution to the Baxter equation, which is left non-distributive, which I will call R, just to fix notations. And out of this solution, I will construct a bunch of reflections. What is a reflection? So reflections, which will usually be denoted by K in this talk. So a reflection is a solution to the reflection equation, So solution to the reflection equation associated to R. So all these things come from physics. Whenever you have a linear solution to the Baxter equation, you can consider the reflection equation associated to this solution, and you can construct its solution. So I will explain a little bit where it comes from in physics. And as usual, as it was done by Greenfield for the Baxter equation, one can try to simplify things and first to look for theoretic solutions. So I think this equation was brought to the Brace community by Agata Smoktunovich, Leandro Vendramin, and Robert Weston, who published a great paper on this. And there were some more papers before and after this. But all these papers were concentrated on the following question. Given a solution to the Baxter equation, try to find all solution to the reflection equation associated to it. And this is equation useful for physics. And here we completely change the perspective up and do a rather strange thing. So this will be the third part of my talk, and this is the new part, the new thing. So I will, for every reflection, I will construct what I call a generalized derived solution. Derived solution, which I will denote by RK. It means that I have actually a whole family of solutions to the Baxter equations, which are indexed by reflections. And even in small examples, you can have a really big family here. So now I can do the same thing as before. I can try to compare the structure monoids of my original solution and of my generalized derived solution. And as you probably expect, since I'm talking about this, they will be related. Once again, there will be a very explicit map, which is inspired by the map we had in the case of simple derived solutions. It will again be one-to-one. It will be bijective, so that you will have two multiplications on your original structure monoid, the original one and the one which you can pull back from the new one. But the relation is slightly more subtle than we had before. It will be a one cocycle-like map. So it will satisfy some condition which is somehow resembles a cocycle but is not a cocycle condition. And I will write this explicitly. So this means that you will have two monoid structures on the same set if you pull the second structure back to the first one, which will be somehow related. And it will be something which I will call brace-like. So this is really the whole message of this talk. So if you are used of thinking about solutions and their derived solutions, what I'm trying to present here is that actually the derived solutions are part of a whole family of generalized derived solutions. So there is a whole variety of solutions related by some bijective oncocycle maps in the story. So two basic examples. Examples. So first, you will always have the identity map, which will always be a reflection. This is simply the R prime. By the R prime, I denote the derived solution. The simple derived solution which you're all used to. And then I will just explain in two words how it is constructed. So you can take your original set, add some artificial element, the star element, and extend your solution to this star element in the most obvious way, and then consider the projection where every element is sent to your star map. It will once again be a reflection, and this generalized derived solution associated to this very degenerate projection will be simply your original solution. So this family will include your original solution, your derived solution, and a lot of things in between. And I will ask two questions before going to details. So the first question is, what is the appropriate structure here? So if you have just a one cycle map, then it gives rise to skew braces. Sorry, I forgot to mention that I was working with skew braces here. Here I have something more general, which looks like a brace, but which is not. And I don't know what the appropriate structure will be. It will be definitely some kind of semi-truss. I don't think it is something which is Jan Baxter semi-truss or something like this. So I don't know what the right axioms are to describe this kind of situation. And there is a second question I don't know how to answer. So here I was talking about monoids, and I don't know what happens for groups. So this is a kind of a strange situation, because usually it's difficult to construct a map like this which connects two new structures, but it's rather easy to describe its properties. Here I have a candidate for this kind of bijective map between the two structure groups on the left and on the right, but we have not been able to prove that it gives and that is well defined and that is bijective. So we strongly conjecture that the things I will be going about are also true for structure groups, but as for now we cannot be sure about it. So these are the two questions I will leave, and if time permits, I will add a fourth part of my talk to this talk, which will be slightly disconnected to the previous ones. I will talk about these reflections for the particular type, for the particular case of involutive solutions, which is the case which was considered in the paper by Smoktunovich, Vendramin, and Weston. And I will try to explain that in this case, reflections are closely related to what I call strange operations. I'm almost sure that they must have been considered by somebody else, but we have not been able to find them in the literature, and I will just explain what strange means. A strange operation is a binary operation which satisfies the axiom A times B times A equals B times A. So if any of you knows anything about these kinds of operations, I would be very happy to learn new things about them. So that's it. And now I'm starting the details. So I'm giving a long version of my talk where I'll explain in detail how things are done. I'm starting with a map R, which will be a solution. So it goes from x times x to x times x as many of you do, I will say that to A and B, it associates lambda A of B and rho B of A, just to make notations clear. And a way to draw this map is just to draw a crossing. So you will have, I will put A and B at the bottom, and your lambda A of B and rho B of A at the top. So, and having this map means that when you have some picture with a crossing, you are able to propagate things from bottom to top. So I suppose that my map R is a solution to the Baxter equation. Again, all this, I will be only talking about theoretic solutions. That's why I'm not mentioning it explicitly. And graphically, it means that, well, you have the Rider-Master 3 move, which has been mentioned already a couple of times, but I will draw it anyway. Means that you can play with your diagrams freely. And I will, my solution will be right non-distributive, which means that all the maps rho B are bijective. And it is very easy to interpret in the language of diagrams. It means that you can propagate colors to the right. So whenever you have some colors A and B here, rho B minus 1 will give you the element here, and then applying your R map, you will get an element here. So in all my diagrams, I will draw in green the colors I start with, and in black the colors uniquely determined by my green colors. And then, so these are the only things I need. And with this, I can construct the what I call the guitar map, which will be central here. Up the guitar. Map. There will actually be a collection. I often forget the index n because it's of elements of x. So a1 u and tuple of elements of x. By the following graphical procedure, you consider this kind of braid, which is something very well known in braid theory. It corresponds to the Gaussite element of the braid group, actually. You put your colors A1, A2, and so on, AN, to the bottom. Then you propagate the colors upwards. You can do it by applying the R map, and you'll get some colors A1 prime, here A2 prime. So you consider the rightmost colors, AN prime. So it actually means that you start from the bottom colors and you read the colors you get to the right. So this is a definition. And this map is very simple to construct, and it's very nice. So first of all, it is bijective, which is obvious because of this right non-degenerate property. It tells you that the colors from the right can be propagated all the way to the left, and you can get the bottom colors like this. And a far less trivial property that if you first apply your solution R to the position I and I plus 1, and then apply your map, your guitar map, you get R prime applied to the position I and I plus 1, preceded by the guitar map, where this R prime is the derived solution, which is very easy to draw. I draw it like this, and you have also seen this in some talks yesterday afternoon. So I start with the colors A and B here. Since I'm right non-degenerate, I can propagate them to the left. I can get some colors here. Then I apply the R map to get the colors here. And I will call C the color I get here. And so my R prime of AB will be simply CA. And when I'm writing the index I mean just that, well, since I'm working with the n tuples, I can apply the map R prime to any two of the components, and I'm choosing the components number I and number I plus 1. So this means that your R map and the derived map R prime are the conjugate of one another by the guitar map G. So where does the map guitar comes from? If you have a lot of imagination, this picture can be seen as a picture of the guitar strings when you turn your guitar like this, and when you're looking in the profile at the profile of it. So this property can be proved in a very, very simple pictorial way. I will try to to show it. It will be here. So in the first picture, you see what that you first apply the map R at the positions you like, and then you apply the guitar map. You're looking at the rightmost colors. And then this crossing, you can push it like this to get the second picture, and it will appear here. You can push it because of the rider master move, because of sorry, I somehow got disconnected, so I'm reconnecting my screen and I will continue talking. So using the rider master 3 move, you can push up, just sorry, I will need some time just to reconnect.
I think you lost your host privilege.
Yeah.
So I need to. I will make you co-host and then.
Thank you. Sorry about that.
Or you or your screen. I don't know which.
Yeah. That's it. So up. So in the first picture, I applied first the R map, and then I pushed it upwards using the rider master 3 move. And so this is where my my crossing appeared. And then I then I take another crossing, which is the upper one, and then I pull it away once again using the rider master 3 move, and it will appear here. And by looking carefully at the colors on the right, I will understand that what happened will be precisely the application of this derived solution. So this is in 3 pictures you have the whole proof. And this is this property is everything I need to have quite a lot of nice corollaries. So first of all, it gives me directly that R prime is a solution, because from the construction by a picture, it's not clear at all that it will satisfy any nice properties, but it will be a solution to the Baxter equation just because your original solution R is, and they are the conjugate of one another. Then it gives you also for free that your original solution is invertible or involutive or idempotent, if and only if your derived solution R is such. So is invertible or involutive or idempotent, just because one is the conjugate of another. It also gives you that your solutions induce isomorphic actions of your braid group on an elements or braid monoid, depending on whether you're working with braids with groups of monoids, on the powers of your set. And it gives you that your Gita map induces a bijection between the structure monoids of your solutions, or if you have some more technical conditions between the structure groups. And with some more work, you can show that it will actually be a group or monoid Wanka cycle. And the last point is clear because you can see this one of the ways of looking at the structure monoid, or similarly at the structure group, is that it is the free monoid on X, where you say that where you mod out by the condition R map is equal to the identity. Since the R map and the R prime map induce isomorphic actions of the braid group, when you mod out, you get isomorphic, you get bijective monoids. So that's the whole story. And now I will talk about the reflection equation, and we'll see. So the advantage of this graphical approach is that there is very little input you need to get all these useful corollaries. And I'll start with a definition. I'm still working with a solution R. So I have R, which is a solution. And I can see the maps K from X to X. I'm saying that it is a reflection for my solution for R if it satisfies a strange identity RK2 equals K2R K2R. So all the things are maps from X times X to X times X. R is a map which goes from X times X to itself, so it's clear. And K2 it means that you apply the map K only to the second component of it. There is a kind of a strange commutativity relation, which is called the reflection equation. And I will write RE for the reflection equation, and it comes independently from two domains. First of all, from physics. I will show you a picture. Up. Up. So if you think about n particles moving on a line, if you can consider the collisions between the particles, you will naturally think about the Yang-Baxter equation. So this is what the first picture is telling you. So here I'm drawing just the paths of my particles, where the time goes from bottom to top. But if instead of working on a line, I'm working on a half line, it means that I introduce some wall on the right, which you can see here, and it means that your particles can go close to the wall and then bounce off from your wall. This will be the bouncing trajectories, which you see in the second picture. And the reflection equation means that the bouncing order is not important. So you can have, on the right, you can have the second particle bouncing than the first one. On the left, sorry, on the right, you have the first particle bouncing and then the second one, and the result is the same. So this is the meaning of the reflection equation. But you can also see it in topology. And I will need another picture for this. Up, which is here. Up. Up. So I'll draw this reflection equation where the K map will represent the K map, the reflection map will represent a strand of your braid going around a fixed pole. So this is typically a situation where you consider the braids not the usual braids, but the braids on a annulus, and where this violet chord represents the core of your annulus. From this point of view, it's also a completely natural condition. Now, as I said, there has been quite a lot of work on trying to construct different families of reflections given a solution to the Baxter equation, and on trying to classify them in some sense. This is a very difficult question because even for very simple solutions, you have plenty of reflections which can have a very difficult behavior. And now, but what we have done in our paper goes in a completely different direction. What we have done was trying to repeat the whole story of the guitar map, but adding adding a reflection. So I will try to copy this. Sorry, I was not efficient. Should really start to the left. Copy. And I'm not able to paste. paste. Up. So what I will do now is picking a new color up and add some up the key maps everywhere. So I will define, I take a k which is a reflection for a given solution to the Baxter equation. And then I will take k geta maps, which will also depend on a reflection by the same picture, but I will add the maps k everywhere. So when I put a dot on my picture, I mean that I'm applying a map k. And so I have this picture, everything can be constructed because I have the k map, and I read the colors on the right just below the application of the k map everywhere. So this up, since I'm starting with a right node degenerate map, I can read all this in backwards. So I will get some one-to-one map, and I will have a similar condition here, but instead of the derived solution, I will get a generalized derived solution which depends on k. And I will now show how to construct it. So I'm having this picture up. Up and here. So I'm considering simultaneously these two pictures. Then I put my colors A and B here. Up. Then because of since I'm right not degenerate, I can construct a color here. Then I apply the map R to construct the color here, then a color here and here. So suppose that here I have some color C. Then on the right picture, I start with C and B. I propagate everything upwards, and I get some colors which I call B prime here, just below the application of the K map, and A prime here. And so my, instead of the derived map I got here, I'm now saying that RK of AB is the couple B prime and A prime here. So it's as simple as that. So if you just look at this construction, you can ask yourself, well, what can it be useful for? Why considering such strange things? But the point is that the theorem we got in the case of the usual Gita map and the derived solution still holds. And the proof will be completely analogous. You follow the same picture. You just add some dots here corresponding to the reflection map, and everything works perfectly. And from this, since the proof works, you also have the corollary, which up, sorry, up, which can be really copied once again. Up. Up. I'm not very good at this. Up. So you new maps will all be solutions. They will be invertible or involutive or idempotent if and only if your original solution is. They will induce isomorphic actions of the positive Braidmanoid on powers of your set, and they will the Gita map the K-gita map will induce a bijection between the structure monoid of your original solution and the structure monoid of your generalized derived solution. So this explains why you have this bunch of related um, related solutions and bunch of related monoids. And I promised you to explain in what way it is one cocycle like. I will write precisely what it means. So you can ask yourself what happens if you apply your K-gita map to a product, to some A times B. I put a bar because these elements of these are some n tuples of elements. So it will be similar to a group map, to a monoid map, sorry, except for the thing that this A will be, the A here will be in some sense be acted on by B, in the sense that you have rho of delta of B applied to it. What is delta? Well, you start with some n elements of your set. You consider once again the picture you had, the picture of this, what is called Gauss-8 element. You put your K maps everywhere here on the right, and at the top you have n elements which you will call rho of A1 and so on an. So it is some map closely related. It will be an n tuple closely related to the original n tuple. So this is the delta map, and by rho, so the rho comes from the original solution, but you can extend it from x to the powers of x in the straightforward way. When we were working with usual derived solutions, so this was actually an action of the B itself. It can be transformed to the action of B itself, and it can be pushed on the exterior of the gita map, which gives you precisely a monoid one cycle. Here, neither the first nor the second thing can be done. So it remains this way. And so as I said, the most important thing for us is this one. You have a bijection between these monoids, which satisfies some strange relation, and I would really be eager to understand what brace-like structures are involved, can describe the situation appropriately. And now there are some more things which can be mentioned. So one natural question will be, can we iterate this construction? What do I mean? If you take your right non-degenerate solution, if you consider its derived solution and the derived solution of the derived solution, you get just the derived solution. So there is no point in deriving a solution several times. It doesn't give anything new. Then in general, if you consider this generalized chi-derived solution and you take a reflection for this new solution and use it to construct one new generalized solution, it may yield something new, yield new solutions. So the situation is much richer and much more complicated here. but our computer experiments show that the situation tends to stabilize very fast. So at some first iterations, you may obtain new solutions, but starting from some point, you get something new, you get nothing new. And one of possible reasons for this is the following. If you consider the derived solution and the derived solution of the derived solution of the generalized derived solution, they will be the same. So this is one of the theorems we have proved. So really these original solutions and generalized derived solutions are closely related. And I don't think I have what I will do now is just mentioning some last quite curious result. So you can consider the following picture. Up, where you apply the map K here. You can start with the colors A and B as usual here. This can be used to construct a color here, which I will note by A, black triangle B. And I will put a K here to show that it depends on K. And one can show the following nice fact. You can consider the operation B times A, which is just this A black triangle KB. So this is just to let B act on the left rather than on the right. And this extends to an action of the monoid, of the structure monoid of your K-derived solution to on X. So this is a very usual thing in the when you're talking about the Baxter equations. So almost everything, all these groups or monoids which you construct, they will act on the original set. And so here we have a bunch of generalized derived solutions with a bunch of structure monoids, and each of them actually acts on the original set X by this map. Just for an example, if you take the identity map, then this map will just be the quandle map, which is as usual constructed out of a right now degenerate solution. So I think it's better to stop here. I don't really have time to talk about these strange structures, but well, for me the most important point was just to mention them in case any one of you has come across these structures and can share something about them. So thank you very much for your attention.